Hi, and welcome to another Hopper on 6502 video. This time round, I've built a little operating system for my single board 6502 computer. And by little, that's an 8K EEPROM. So 8K EEPROM, 64K of RAM. But I've got it configured using my CPLD for the address mapping, so that I've got 56K of RAM and 8K of ROM. Okay, so that's what's on there. This little BIOS, it was based on the work I did on Hopper Basic. So I came up with that. I wrote quite a tight library for heap management, the file system, all sorts of things. It's integer, arithmetic, floating point, all that. So I wanted to see how small I could make it and see if I could squeeze it into an 8K ROM, which I did. And it's got, it's sort of DOS-ish, it's got a dir and you see your directory. It's got a clear screen. There's a mem command. There's an upload command called IHex where you can upload a binary via the serial port, so that you can, because it's kind of hard to initialize this. This is the EEPROM, this little 8-pin chip here. It's hard to get anything on it initially. And I do have I'll just give you a sneak peek. I've got a substantial application too. I've written an editor. And this is a full screen editor. In the sort of spirit of the Turbo Pascal editor, which was a WordStar editor and WordStar keys, but I'll get to that later. Okay, so let's go and have a little bit of a look at what Hello World looks like in this universe. Okay, let's move you aside. So here's a Hello World application. I really need this to be bigger. I'll pause the video. There, that's better. Now you can see what I'm talking about. Anyway, this is your classic Hello World. It's got a string constant, loading the string constant up into zero page pointer to string, and then it's calling a system call to print the string. So let's walk through how it works. So if we right click on print string, it's doing a API dispatch into the BIOS, the operating system, and the operating system is sort of in the spirit of CPM, in that you dispatch your calls through a single interface. In CPM, I think it's on the Z80, it was like an interrupt, but we don't have that, so we're doing it through a jump to an address that is stored in the 0 page, so that the BIOS can be moved around if we want to in future. And if you want to see what all the BIOS calls are, if we right click on print string, we'll see here's a list of all the BIOS calls. So into this little 8K BIOS, what have we got so far? We've got the heap manager, we've got the file system, serial IO, which includes some useful print APIs. It's got a time API with a delay and a tick, like a milliseconds tick or a seconds tick. It's got a 32-bit integer library, and it's got a 32-bit IEEE floating point library. And this is optional. So if I exclude this, I gain about a K and a half of space in my 8K ROM, which is going to be handy if I want to extend it. And you could always include this in your app instead of in the operating system. And then it's got GPIO, sort of, because this board has got some pins on it and the GPIO stuff. So let's go back to Hello World. So that's our Hello World app. So how does it work? So in here, we've defined a constant, or defined a symbol, Hopper BIOS applet, and this tells the assembler, which is not really an assembler anymore, it's an optimizing compiler for 6502 assembler. It tells it to build this as a Hopper BIOS applet, which means it doesn't have the usual entry points. I'll show you what it does. So if I build this, it optimizes it. So let's go and have a look at the assembly that generated. Okay, so here's Hello World, and it did a function call to print string, but it did a tail call optimization here because it was a function call followed by RTS, so it just converts it to a jump to here, and then this RTS returns. So how does this work? When the BIOS loads this into memory, it loads the app at 800 hex. So like CPM, it's at a fixed address. It's not relocatable. And this is our hello world string in the constants array. And all I did is modify the assembler to insert 3 bytes in the front of the constants, which is the beginning of the program. Because the way the assembler works is the constants always went at the beginning. So I had to do a little hack here. And that 4C is a jump instruction. So the BIOS will load this, and then it'll do a call to this address, and then it'll just jump straight to 8010, which is the start of our program, execute our program, and then when our program ends, it does a return, and it returns back to the BIOS. So when the loader loads this, it loads it at this address, and then it reinitializes the heap to be all the memory above this, which in our case is close to 54K of RAM or something on the heap. So you've got a massive heap. Anyway, and then when it finishes, it exits and goes back to the BIOS. Okay, that's how a program is compiled. So there's no usual interrupt service routines or entry points, start entry point that you'd expect in a 6502 assembly program, because that goes to the BIOS, not to here. Let's go and have a look at the hex that was generated by that. So this is the IHex that was generated. That's the code, Intel IHex format. So let's copy that onto the clipboard, and then we'll switch to our device. So this is my device across the serial port. I'm using PuTTY, a sort of a VT100 compatible serial terminal. So here we are. I've already got a hello, but we'll make another one. So the hex command, I'm saying I'm going to upload hex into hello as a binary. Overwrite the existing one, yes. And then right click here to paste. And that was quick. It uploaded 33 bytes. So now I can run hello. And like I said, so what this is going to do is the loader will load this to hex 800. It'll then reinitialize the heap to be above that. And then it'll call to this. And then when hello is done, it'll exit and return to the BIOS. Let's try. There we go. Hello world, and it returned to the BIOS. Just like that. Pretty cool. Other applications that I've made in the sort of hello world frame, let's have a look. The usual blink. So what does blink do? It's using a few more APIs to demonstrate the APIs. So this pin write, so if we look, that'll be dispatched as well. Pin write, pin read, pin mode. They will get dispatched to the BIOS as function calls. It's doing a delay. And we've got these 32-bit variables that we use a lot, top and next. It's like top of stack and next of stack, and delay takes its arguments in top. So there's delay dispatching, and they all have these detailed comments explaining how they work. Like delay will take milliseconds in a 32-bit integer on the top of the stack, or what they return. So the output from millis is a 32-bit integer, or the output from seconds is, it's a 32-bit integer, but it's millis divided by 1,000 basically. Right, so these are the APIs for that. So let's go have a look what blink does. I've already got it on here, so we just run blink. And it's going to do exactly what you expect. And then Control-C does that. Now, interestingly, Control-C also, I've hooked up to the NMI, so I could do that with the button too. So let's do that. And all it does is, it converts, it's an unstoppable, to wait until the light's off. Like that. So it's the same as Control-C here. And the little dots are 1 every second, I believe they were. Okay. So that is how you write little applets for my little operating system using my compiler toolchain. And then the applet that I've written, if you grew up on Turbo Pascal and WordStar, then you're familiar with these keys. So this is the navigation diamond on the left of your keyboard is these ones on the left here, the cursor movement. And WordStar predates, like the Microsoft Office standard, cut, copy, paste, the clipboard, all those keys. So there was no concept of a clipboard when WordStar was created, and Turbo Pascal was in the same generation. So they had this idea of a block or block operations, but it's not the same as the clipboard because it actually persists between instructions. And yeah, if you type, it doesn't wipe it out, all that sort of thing. But in the modern era, and also this was invented before there was an extended keyboard. There were no arrow keys or home and end and page up and page down. So they had to use all these control keys, which means they used up control keys that we associate with normal things like select all or cut or copy or control S for save or control O for open, that sort of thing. So I have done this, so I can go, you see, I don't know them very well. I think it's Control K open for reading or something. Yeah, open file. So I can load a file like that. But I don't know these keys that well. So let's exit out of that. And I've got another version of the editor. And this version of the editor, it's in the spirit of the WordStar shortcuts, but I've swapped out the cursor movement for arrow keys and page up and page down and all that. And then that lets me use the sort of modern clipboard keys and Control S and Control O and all that, right? So now I can do the same thing again. I can go open, I've got Mandelbrot source, basic source here, so that we've got something interesting to edit. And it's got a status line at the bottom of the screen. It's this is a 80 by 25 screen, even though my terminal's bigger than that. And the 25th line is used as a status line. So page down, go to the end. And it's got, so Control Y is a delete line function. So if I go, I'm on this line and I go Control Y, we lose a line. And then I've got a modern undo. So Control Z does the undo. And then you can do the block thing too. So you can go Control K, and you can see the key light up there, Control K B, go to the end of the line, Control K K. And then I can say I want to copy that with Control C. So this is a hybrid. It's like put that on the clipboard. So it moved it to the clipboard. And I can go here and go Control V and it'll paste a copy, right? And then undo, get rid of it. Okay. Anyway, so I'm scrolling the wrong window. It's funny thinking the mouse wheel's going to work and just scrolling the terminal. Anyway, exit out of there, dir, mem. So that's my little operating system. That's it in a nutshell. So, and if this thing takes command line options as well, so I can load up a file like that. Yeah. And it's, there's a couple of interesting technologies in this. The first is I'm double buffering the screen so that, because I'm using VT100 codes so that I can go to a coordinate on screen, go to a position, draw something, and you might notice that the bottom line is in bold. So I can write out a file here. If I go KW, it'll write out a block, write out that print as a file, export to. So you can see the bottom is in bold, especially if I just write out one. You can see them next to each other. And now if we go exit and dir, we should have a small file called print. There it is at the bottom of the list, 5 bytes. And now we can go edit print. And it should have one word in it, print. Yeah. So, and then we can demonstrate the delete command. And print should be gone. Yeah. Anyhow, interesting technologies in this. So first things first, I've got a double buffer for updating the screen. So if you make a change, it doesn't send the whole screen. It only just it sends the change you made, just the small change. And then the second thing I've done is in writing this editor, I've used something called a gap buffer, which makes it super efficient. It's more efficient than, say, a linked list of lines, and it means it's sort of got single undo toggle. So undo redo is sort of built right into the data structure, the gap buffer data structure. Anyhow, this was the first app that I thought of that would be useful to put on my little operating system, have an editor so that we can actually edit code on the device. And there's a comment in one of my previous videos saying, how do you edit like a large function in Hopper Basic? And it's like, yeah, you don't. You do it on the PC and paste a new one into the console. But now you totally could, edit edit on the device. So what's next? All sorts of apps we could write. So we could write operating system apps, like useful utilities, like a debugger or type command, like show me this file. I think the editor was one of the essential operating system commands, and it's kind of small as well. The Turbo Pascal one is actually smaller than the main editor because it doesn't have a clipboard. There's one more function, a feature I should have shown, which is actually a good way of navigating around and seeing how fast the editor is. So if we use the find command, so what are we going to find? Let's say find, so we go, you try and press Control F for find, and it's actually go to the end of line. So it's actually Control QF. There we go. And let's find print. There's the first one. And then find next is just Control L. So Control L keeps finding the next one, and it keeps saying found. There should be some more near the bottom. There, jumped, and then it'll find the ones in the intro, and then now it says not found. Yeah, pretty cool. So I can go to the top again, QR, goes to the top of the file, and then L keeps finding again. So find and replace. Good way of proving that the scrolling works. And that it's pretty zippy. This is an 8 megahertz 6502. Anyhow, apps to write next. I like this idea of being self-hosted, of being like, once you've got your BIOS and your key apps installed on your little tiny device, you could just develop on the device, just plug it into a serial terminal on anything and just develop. And once again, I'll put links in the video to where you can get the hexes for this, because if you've got one of these boards, you just burn the hex onto the 8K hex onto this, and you've got your BIOS done. And then you might want some programs, so I'll supply the editor, the hex of the editor as well, so you can upload that as well. And that's basically a fine starting point. Is to you really just need an editor and the BIOS, and that's a good place to start, because everything, of course, is on the GitHub, but the links to these binaries will be kind of useful. Yeah, and look forward to comments again. And in the comments, why don't you put in some suggestions as to what applications would be useful to write next? I mean, you could just write games, like make Tetris work or something. But I like the idea of, but that I'd be developing that in the Hopper assembly, to write another game like that. I'd rather write an app that allows us to work on here, like a fourth implementation or a, 6502 assembler or disassembler, something like that. Anyway, give me some suggestions in the comments as to what the next app should be. And there's so much room. I mean, it's got 55K RAM, and there's 41K available on the storage, on the file storage still, because only 10K, well, I've used 20K because I've got the editor twice, but really I've only used 10K for the editor so far. So an editor and some kind of language tool would be kind of cool. So I think assembly would be the interesting place to start. So make a little minimalist assembler that it doesn't have to disassemble generic 6502. It just has to assemble Hopper BIOS applets. So it has to be easy to dispatch the calls to the, for the functions of the operating system. It has to be easy to assemble something that sticks to the pattern of needing to be loaded at 800 hex and having a return at the end, that sort of thing. Yeah, so an assembler and a disassembler might be interesting. Anyway, thank you for watching, and I look forward to your suggestions.